Swayam Prabha. Digital India. Educated India.
Welcome to this 12th and last Gian lecture on high-fidelity Lattice-Boltzmann methods. So we've gone through all the theory of the method itself, and today we are talking a little bit about the algorithms that are implemented in order for all of this to actually work. So there is this observation that having the idea of, for example, using cumulants in the collision operator and then actually doing the thing, implementing the thing, is a big difference. To be honest, the first implementations of the cumulant method did not produce any advantage. First of all, they were extremely slow, and then we were not able to observe that there's a real improvement or that there's much improvement. And the reason for this, we figured out were the round of errors in that method. And now, of course, after some time, we, of course, solve these problems. So, but let's get us familiar with what the problems actually are. So first of all, we very simply have more floating point operations. So you already in the hackathon, you noticed this by just using the central moments. We have more floating point operations in the cumulant method than in the BGK method, for example, and also more than in the MRT methods. So this has, of course, two consequences. The first of all is that this should be slower then. I mean, you do more work, yeah. As it turns out, this is not necessarily the case that the cumulant methods. I'm not completely sure whether I'm too loud. It sounds a bit strange. Myself, I'm turned off. Yeah, okay. I am trying to speak a little bit less loudly. Yeah, actually, the compute time does not increase that much as you would expect, or not necessarily. It depends on how you implement this. The reason for this is that on a modern computer, so this was different when I was young, yeah, but nowadays the memory access is much more expensive than the calculations. Actually, in terms of memory access, we are on par with the BGK method because we only have to read our populations, yeah, and then they are usually in the processor and in the registers while we are doing computations on them. And so these operations are not necessarily then expensive. What you can do with a clever implementation is an overlap. So you can use overlapping floating point operations with memory access, and if you do this and your memory access and your operations are not too much actually, computation can be more or less for free. So in a method where you don't have a lot of computation, like the BGK, if you leave out the computation and just do the streaming, you almost have the same execution time. Yeah? And if you don't add that many operations, then also the execution time will not change a lot until you come to the point where doing the computation is more expensive than doing the memory access, and then it's governed by the calculation. So usually we distinguish between these compute-bound algorithms and bandwidth-bound algorithms, yeah? Depending on whether the memory access is the more expensive part of the algorithm or the computing is the more expensive part of the algorithm. And LBM usually is memory bound or bandwidth bound. So bandwidth, the bandwidth of how quickly you can move memory information from the main memory into the processor and back. So it's bandwidth bound, or we can also say limited, meaning that the memory access dominates the execution time. And this usually becomes different with the cumulant method, because the cumulant method can be, but does not need to be, depending on the implementation and the computer that you have. Cumulant method can be compute bound or compute limited. So it's actually a good thing for the cumulant method that it's pretty much on the edge between communication and computation. Yeah, so this means it uses both things. I mean, both the processor and the bus it's making good use of both of them, you could say. Yeah, while a BGK method for the BGK method, the processor is actually too fast. Yeah, the processor will starve for information because you have to load all these populations, and the amount of computation that you do is only small. So this is one thing, usually the thing that you see first, because you immediately recognize how fast your program is. A thing that you notice only later, but which actually is more important, is the accumulation of round-off errors. If you have more operations, then you have more accumulation of round-off errors. At least in this type of method. Maybe OpenFOAM doesn't have this problem. What kind of algorithms do have this problem, and what kind of algorithms don't have this problem? Any idea? The Lattice-Boltzmann is completely explicit, even though we can reformulate it as implicit, but the algorithm is completely explicit. Yeah? So many numerical methods use implicit method, where you have an iterative method to reduce a residual error. Yeah? And for these iterative methods, it does not really matter where the error is coming from. So the error could be the residual from the last iteration, but it can also be the round-off error. So this is all summed up, and then it will try to reduce the round-off error from the last iteration. However, whenever we have a completely explicit scheme, then all the round-off errors that we do are just stacking up. Yeah? So and this is here a problem of the Letters-Bosman method as a completely explicit method. So, and therefore we now try to understand the two different aspects of round-off errors in this method. Understand round-off. So always try to understand your problem before you try to solve it, yeah? And tell this your doctor. Okay, so there are two problems that we have to discuss. The first problem is the data loss in storage. So this does not have anything to do actually with the computation itself. So we have data loss in storage. And this is related to the way we store our information in the populations. So we have the populations. Fij, say in 3 dimensions. So they are superpositions of moments. M, A, B, C. So they are also combination of cumulants, but I'm now using this raw moments to indicate that they are actually simple superpositions, so simple sums of them. For cumulants, they would be a more complicated function, but for this is just each population is a weighted sum over all the moments, right? So meaning you can always, so for raw moments, yeah, you can always write it like this, that any population is a sum over A, B, and C, and there must be now a weighting factor, alpha I, J, K, A, B, C. So this has now 6 indices, obviously, yeah, but each of them is a constant. So each entrance in this tensor is a constant, and thus you have to multiply with M, A, B, C. So there is a fixed transformation from the moment to the populations. So each population contains each of the moments. So what does this mean for the storage? Let's look at how we store our variables. So they are stored, of course, in floating point numbers. And say a floating point number, though there's different formats, but just for the purpose of this discussion, they are not that much different. Actually, the funny thing is they are actually different, yeah. And this actually makes problems for reproducibility. For example, like, I don't know, somewhere 8 or so years ago, NVIDIA changed the format of the rounding format of their floating point operations. Yeah, so they are not necessarily all the same. So let's say we are following the IEEE 754 standard, and we'll discuss this for 32-bit float. And you have to know, while in academia, we like to have high precision and often use 64 or larger data types. The most of the actual simulations that are done in industry are done with 32 bits, yeah, or nowadays even lower. I mean, the graphics cards, I don't know whether you noticed this, but they become lower and lower precision all the time instead of higher precision, yeah. By the way, the first computer that was ever built, the SUSE 1 in the 1930s, already had 32 bits. Floating point operations. Okay, so we need a new page. So how does this thing look like? So we have 1 bit for 1 bit as a sign. So whether it's a positive or negative number, then we have 1, 2, 3, 4, 5, 6, 7, 8. We have 8 bits. The exponent, and then we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. Okay, so this is how it would look like. I don't know whether I miscounted this. So 23 bits in the fraction. This is where the actual information is more or less stored. Yeah. So 1 number has only 1 exponent. Yeah. This means that all moments share the same space in the fraction. So this is a problem because the moments have different scales. This is something that we know now from asymptotic analysis. So they have different asymptotic scales. I mean, this is also true for the Navier-Stokes equation. The variation in pressure is asymptotically smaller than the variation in velocity, right? So now we can assume again different scalings, but as we like the diffusive scaling, we use the diffusive scaling here, saying that delta t is proportional to delta x squared is proportional to epsilon square. And then we see that there are, for example, in epsilon to the power of 0, we have the density. So this is the 0 part. Epsilon to the power of 1, we have, for example, velocity. So this would be E times the physical, no, not the physical, sorry, times the first order, yeah, the solution of our velocity here. And then at second order, we have the pressure. So the pressure in the sense of the pressure variation. In the Navier-Stokes equation, we only care about the pressure variation. There's a background pressure that is constant. This we don't care about. Yeah? And so the pressure is then epsilon square rho second order, and in principle you have to multiply this by theta, yeah, in order to make it a pressure. So, and you know, the rest, you also have, you know, some errors that So these things here is maybe the error, yeah? And this here is the solution. So this is what you want to have. So our problem with all of this is I don't know, is this maybe a little bit better? Yeah. Yes. So the problem with all of this is that since epsilon to the 0 is much larger than epsilon to the first order is much larger than epsilon square, and so on, these variables are, as we say, scale separated. Again, this is also so in the Navier-Stokes equation, but here we store these things together because they share the same space in the fraction. And this causes problems. So let's really look at this. So say we have here our fraction. The fraction of our floating point number, and say we have here our most significant bit. And we have at the end the least significant bit. So how is our information stored? The largest thing that we have is rho 0. So this defines our exponent, and this means it defines the first number in the fraction, yeah? And this thing is then stored. So this has all the space it needs, right? So then there is something smaller by epsilon. So this is U1, yeah? U1 is by definition smaller than rho 0. So this thing can occupy this amount of memory. Then, after this, we have something that's even smaller, yeah, namely, see, this is 4, like this here. So this would be theta times rho 2. This would be the pressure, and also we have the stress. The stress is also of second order, yeah? So these things, this kind of information, can occupy this amount of memory. And then, in addition to this, we have our ghost moments. So the ghost moments come at different order, but say we're looking at the ghost moments at the third order, then they only have this amount of memory left. And this here is the effective number of bits available for each quantity. So we see that, I mean, this has nothing to do with their asymptotic precision now, yeah? Even though, okay, it has something to do because things are, when they are higher order, So they turn out to be smaller, yeah. But asymptotic analysis always assume that the precision, the numerical precision that we have, is infinite. Yeah, but in reality it's finite, and we see that, for example, for the pressure and the stress, we have much less space actually to store it than for example, for the velocity. And these differences here, they are scalable. So if you start with a smaller velocity, yeah, these other things become yet smaller again. So let's just make an example. So say we have rho to 0 order is 1 and u is 0.01 delta x by delta t. Then this would mean that theta rho 0, yeah, this is of the order of u square, which means that this will be something like 0.001. And if this here is smaller, say 0.001, yeah, this would become 0.00001. Okay, I did not count correctly, but yeah, it becomes the square of this. Yeah, so it becomes worse and worse and worse. So this rho 0, this is largest. And it defines the exponent. Of our float. This means that rho 0 is stored, if we are in 32 bits, it's stored in all 23 bits. Actually, the leading bit is not stored, yeah, because it's always assumed to be 1. And therefore, this thing looks like this, rho 0. Okay, I'm trying to write it down. Maybe I'm making a mistake, but it's only for getting the idea, right? So it's 1, 0, 0, 0, 0, 0, 0, 0, 0, 0. This is 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, binary. So this means it's a binary number. Now you store to the same exponent u divided by rho 0, which is 0.01 in decimal. So this becomes then 0.000. I hope this is correct. 000, 000, 000, 101, 000, 111, 1011, 0000. So don't worry if you don't want to write this down. This is not important. Just get the idea, right? So the problem is here you have lost 7 bits. 7 bits lost. Theta rho 2 divided by rho 0. Say this is now 0.001. Then this appears to be 0.00000000000, which, if I had done this correctly, is 14 bits lost, and you have only left 11010000 0, 1, 1, 0 binary. So you see, you have already, I mean, this is not a terribly low value, velocity 0.01. Yeah, you have you have lost more than half of your bits already for the pressure. Actually, you're only half precision anymore with this. Okay, today is potentially a little bit too much text, but this is on. So in this case, 7 bits of the fraction are lost at each order. So the next order would have then, what is it, 21 lost. You see there's nothing left, yeah? Are lost at each order of epsilon. Of course, the number of bits that you lose is a function or depends on the magnitude of the value of the first value, so the epsilon 1 value. So I may have told you or not that you should start with U1 as small as possible in order to reduce the numerical error, yeah. But now you see, with numerical error, I mean the asymptotic error. Now we have a different kind of numerical error, which is the round-off error, and this actually increases the smaller you make U. So you have two things that go directly opposite to each other, yeah. So meaning, you have been told that making this time step smaller improves your result. Now I tell you, making the time step smaller makes your result worse. So the smaller the time step, the smaller is U when it's delta x by delta t. The even smaller are the higher moments, like pressure and stress. Oh. You can come, it's just already the 12th lecture, yeah? I looked a little bit out of place, actually. So, let's briefly look the maximal ratio of smallest to largest variable. So suppose we represent this by 1 bit, which of course doesn't make any sense, but let's assume this is of course 2 by the power of 23, which is something like 8,388,608, if I'm not mistaken. Yeah. So if two variables have this are different by this amount of numbers, so there's actually nothing left. So for example, EU1, suppose this is 10 by the power of minus 4. Yeah. So what it can be, I mean, it can also be on top of something else. I mean, you have a small vortex inside a large vortex. Yeah, and the relative velocity of the small vortex compared to the large vortex is 10 by the power of minus 4. And now you are interested in whether you can still see the centrifugal pressure of that small vortex, yeah, which means this would then be pretty small compared to everything else, yeah, because this would be epsilon square rho theta rho to the second order, and this would be 10 by the power of minus 8, which is much smaller than 2/23. So this means if you have a small vortex and a large vortex, and you want to see the pressure drop inside the small vortex, you see nothing, okay? Just because it numerically doesn't exist. So, and I mean this is not a theoretical thing. This is something that we observed actually. I mean the problem is kind of the following. So these flows delta x by delta t. Such flows have no detectable variation in pressure. So I remember some 15-ish years ago, yeah, when we first implemented, when we had the first bigger graphics cards and thought now we can do this really large-scale simulations and convergence studies. Yeah, we're using smaller and smaller velocities to actually get accurate results. I remember this occasion that we pretty quickly came to the point where we still got a nice velocity field, but we hadn't had any pressure at all, simply for that reason. Yeah. So and this hasn't been a problem before, simply because the computers were so small and so slow that you had to use long time steps, and you had to use coarse grids. Yeah, simply you could not afford otherwise. Now you think, now we can afford it, and you see nothing works anymore. Yeah? So you have to think much harder then. Okay, so this is a real world problem. As with most problems, you cannot solve this completely, but you can do measures, and actually the measures that are the most useful, or the most that give you the most outcome, are also the measures that cost the least. And one thing that costs the least, or almost nothing, is this conditioning. Should write properly, conditioning. So now you have gotten used to my dyslexia. So what is conditioning? Conditioning is the reformulation of a problem in order to minimize round-off errors. Okay, maybe a mathematician would not completely agree with my formulation, but for the purpose of this discussion, this is what we mean. So, the simplest thing is the most successful, and the simplest thing is, I've mentioned this yesterday, simple measure. This rho 0 is constant, yeah? So if it's constant, then there is no need to store it. Right? So now let us define delta Fijk is equal to Fijk minus Wij. So Wij is the weight. The weight that we see also in the BGK collision operator. So the lattice weight. This is a constant, this is important. Yeah? That is weight. And it's usually defined that if you take the sum over these weights, you have this constant part in the pressure. Now if you store instead of F, you store delta Fijk. You look at the fraction, again with the most significant bit here in the beginning and the last, not the last, the least significant bit in the end here. So what you now store in the beginning is actually, no, not epsilon, is actually U1. Yeah, so then on the next scale you have theta rho 2, and here you store the ghosts of third order, and here this is now the amount of memory available for each of this. So these are the effective available bits, which is now largely improved. So I have a warning concerning this because I've explained this to many people in my life and have discovered that even though it's easy to understand, there is still an easy way that you can make a mistake, a terrible mistake here, yeah? Because this is not, so it is not only the storage in the main memory that we are talking about, but each step in between all the calculations itself is a type of storage, yeah? And when you lose bits, they will never come back. Meaning that you have to guide all your calculations at all times, without any exception, yeah? All the time, keeping this state the same. So, I mean, it is really tempting if you have then the collision operator and you need to do some operations there where in the usual way, say, then it's really tempting to use this delta Fijk and simply add 1. Yeah? So if you do this, you've lost all these bits. I mean, sometimes it is necessary for example, you divide by rho, yeah, then it's necessary to add something. But remember, you have to isolate these spots where you're doing this to really the parts where they don't hurt you. So this requires a lot of discipline actually to do this. Yeah. So let's write this down. This is essential. I mean, as long as you care about round-off errors. Yeah. I have to admit that I'm also sometimes did it the other way when I have to do something very, very quickly. Yeah. But you have to know that then you killed it. Yeah. Okay. It is essential that the well-conditioned state is preserved throughout all the calculations. Okay, so this is something that you really have to keep in mind, that the accuracy you're working with accuracy of the simulation is limited by big the operation with the least accuracy, because they are in a chain. Okay? A chain is only as strong as its weakest link. So this is something that you have to keep in mind if you do conditioning on explicit algorithms. So all of this was now problem 1, data loss in storage. Yeah. So we have not yet discussed about rounding at all, actually. Yeah. Now let's come to the actual rounding. Data loss in the computation. Okay, so what I'm going to do in order not to confuse you too much and not to get too complicated, we say for clarity, we use the unconditioned populations Fijk below. Yeah, so in reality you have to combine these two things. Yeah, so you have to use the conditioned and you have to use the right way of doing the computation. But these things, yes, so you have to combine them. So let's look at one particular example of doing a computation and say this is the naive computation. The naive computation of the velocity. So how do we compute the velocity according to our definition? We have u 1 over m 0, 0, 0. I, j, and k equal to minus 1 to 1, I times f, I, j, k, right? So this is how you can actually do it. Yeah, you will make a loop, or you make 3 loops, yeah, and you loop over these populations. So this is how you can implement it. So what you are then doing is you do a summation over 27 numbers, actually, of which, I mean, this is one reason why you should not do it this way, but this is not so important, because if you add 0 to something, then usually you don't get any round-off error. Yeah, so this is only, unnecessary computations, but they don't bother you with regard to accuracy. By the way, what kind of operation is the most prone to round-off errors? So is multiplication, say we have multiplications. Okay, we also have some divisions, yeah? Okay, forget about divisions, they are a little bit complicated. But what's about multiplication and addition? Who thinks that multiplication is more prone, produces more round-off errors? Who thinks multiplication? Who thinks that addition produces more round-off errors? Oh. I think you should study this in more detail. I mean, multiplication, okay, in multiplication, these numbers rescale the exponent, yeah? So actually, the problem with addition is that if these two numbers don't have the same exponent, they are just cut off. This is not happening in multiplication, right? So the problems that we have with round-off errors usually come from additions. And the other thing is mostly we don't have long chains of multiplication, but very often in statistics, and also here in the Lattice-Boltzmann method, we have long chains of sums. Yeah? So two problems. First of all, the additions actually make the cutoff, so this is why they are so dangerous. And second, usually they come in longer chains. So the summation is the actual problem. Now we have to model this a little bit, and this may be, people make models of this, but they may be inaccurate because it really depends on whether you add large numbers to small numbers. Yeah, this makes a difference. When they are of the same size, then the number of round-off errors may not be that large. But let's do a simplified version of this. So say summing n numbers has round-off error O of, say, n delta, with delta being the value of the least significant bit. Okay, now you see this is not very accurate. The least significant bit of what? Actually, it's the least significant bit of the largest number in the sum, right? And this is also not, the n is also not very accurate here, because if we sum up n numbers, we do n minus 1 sums, right? So it could write n minus 1, but you know, large numbers, this n plus minus 1 doesn't make a big difference. Okay, so the naive way of making a sum is, you know, you have your items, and so basically when you're calculating your expenses of something, you usually have your items, and then you sum up these costs one after the other. So you're accumulating, right? And there is so there are much more accurate ways to do this, which can be pretty expensive. Maybe you've heard about the Kahn algorithm. Yeah, so the Kahn algorithm is actually a more accurate way of building a sum, but it requires additional bookkeeping information. There is also a way of doing making sums more accurate that costs the same as the accumulation, and this is the pyramid, or so they have several names: cascade, or pairwise summation. So more accurate summation using the same number of operations. So we are greedy, yeah, we don't want to spend more money, we just want to have a better result, yeah. So this is the cascade or pairwise summation. So maybe, I don't know whether I can convince you to do this for your household items, that maybe the round of error there is not large enough, yeah. Okay, before we come to this, before we come to the example of this, we also have to take into account that the things that we are summing up are not all of the same size. Yeah, that's a very important point. And in particular, if we sum up populations, then the different directions usually have a different size, because their weight, that you see in the BGK method, for example, is different. And therefore, you should also group them according to their actual size. Because the worst thing that you can do is to add a small number to a large number. And actually, this is also the biggest problem in this accumulation. Yeah, because usually when you accumulate something and all of these numbers, for example, are positive, any problem? Oh. And all of these numbers are positive, then the value you accumulate becomes larger and larger and larger. And if you add small things on top of this, they may actually vanish. So, I mean, if you don't care, I mean, it being so if you would accumulate something, yeah, so then you should always start from the smallest number and add the largest number in the end, right? And actually, the best way of doing a pairwise summation is also to order your operations according to their size. This is, of course, very expensive, and for that reason, we are now using just an approximation by taking a static order of them, where we say, so usually the F111 is usually much smaller than the F100, right? Yes, so let me write this down. The value of the least significant. So the value of the least significant bit depends on the lattice direction. Due to the different weights. So say we have D3Q27. There we have the weight for omega 111, W111. The weight of this direction is 1/2216. W110 is 1/54. W100 is 2/27. So actually there's significant difference, and W000 is 8/27. Meaning that delta 000, so the least significant bit of 000 is larger than that of delta 100 is larger than that of delta 110 is larger than that of delta 111. So what we are going to do is we separate classes by direction. So, and now let's see how we would compute M10 with the same number of operations, but more accurately. Say we'll look at the classes of all the populations that come with W111. We have the class W110 and we have the class W100. For computing the velocity, we don't have the class W000 because this does not appear in the velocity, right? So let's write here down what step do we have. And as a step number 1, we have here in this class F1 JK minus F minus 1 minus J and minus K. Yeah, so J and K, they come in 4 different permutations. So what we do, we have to do this here. So we have it here. We do this operation twice and this operation. So we have 4 of them, right? So we do 2 of them together and another 2 of them together. Here we have F10K minus F minus 10 minus K. And we have F1J 0 minus F minus 1 J minus J 0. Of these, there are two permutations, yeah, so that we have to do in first step, and then we sum them up, and then we have here again 2 permutations. And this gives us step number 2. Step number 2, where we sum these guys here. We also have 1 permutation of this. This is F100 minus minus 1, 0, 0. They have only one permutation. Yeah? So there's only one such operation. So now, after we have done this, so we always want to sum things that are of the same size. Yeah. So after we sum these things together, we assume that they are the most similar. So we can now sum these together in the third round, and sum this together in the third round here too. And then we come to the fourth round, where now there are no more things of the same class left, so we put these here together. And in the last round, in the round number 5, we add this here to this. And then we have the moment M1, 0, 0, calculated like this. So you see, the number of summands is n equal to 18. So the naive summation, because there's actually only 17, so this has an error. Okay, being more accurate than I was above, it's actually only 17 summations, but this 17 summation give you an error of 17 delta approximately. So this is the model. The pairwise summation, because we went only through 5 steps instead of 17. As the number of steps is actually the upper bound of the logarithm of 18, and the upper bound of the logarithm of 18 is 5. So the error in pairwise summation, at least according to this simple model, is of order delta logarithm of n, which is of course smaller or equal than delta times n. Okay, so you should do all your sums in this particular way. How long do we have the room today? 11, okay. Okay, so this brings us to the chimera transform, which now is a little bit more specific to the Lattice-Boltzmann methods. So in our collision kernel, we actually do a lot of these sums. And one particular case when we have to do a lot of sums is when we compute the central moments from which we then compute the cumulants. Because the cumulant method requires a transformation of the populations from populations to central moments and back. So all of them are large sums, right? And all of them can be improved. So let's look at the naive way of doing this. So we compute our central moments K, A, B, C, as the sum over I, j, and k equal to minus 1 to 1 over Fij I minus u by the power of a, j by minus v by the power of b, and k minus w by the power of c, which means we have 27 populations and times 27 moments. So what you have to do is you have to sum 27. You have 27 times. You have to sum over 27 populations. So basically, you could escape with skipping over because anyway you have to calculate the velocity first. Yeah. So actually you could. So you have to do these four, the density and the three velocities first. Yeah. And then you don't need to do them a second time. And maybe you could skip over these. So, but anyway, this is the most expensive part in the entire algorithm. And also it's the longest sums and therefore the most prone to round-off errors. Most expensive. So it's the most expensive operation both in terms of errors, round-off errors that you do, and in terms of time that it requires. So, question, how to accelerate this? Maybe you have an idea. You may have an idea, because when we published this, the reviewer said this is too trivial for the paper. Let it out. The thing is, good things are always trivial in the end, because I have to tell you, the entire cumulant method worked only after the introduction of this method, because without this optimized way of computing this, first of all, it was incredibly slow. Doing this naive transformation is really incredibly slow. And the other thing is, all the good things that should come from the cumulant methods, they are kind of evened out by the round-off errors that you do by this. So without the Chimera transform, it's almost impossible to do the cumulant method. So it's really an important part here. Any idea how we would accelerate this? Okay, I tell you. So why do we call this thing Chimera? What is a Chimera? A Chimera is half one thing and half another thing, right? And we say this is now part distribution. Part distribution and part moment. So I have kind of a little bit invented my own nomenclature, so I hope you understand this. So let's say we want to transform the populations Fijk into moments, so into central moments. So I write K, but I leave the indices I and j, meaning that I leave populations in direction I and j, and I do the integral only in the z direction. So here I write already c, yeah, because I'll have the integral in the z direction, but not done in the x and y direction. And then we have very, very trivially, as you will see, k equal to minus 1 to 1 Fij k minus w by the power of c. And now this is 27 times, so you have to so that there are actually 27 populations that you have to do this with, but there are three of the moment, so C is 0, 1, 2, right? Okay. Now, very trivially, you just go on and do this for the y direction, where we sum over j is equal to minus 1 to 1. Now we take this, what we just computed, kijc into j minus v by the power of b. Yeah, again, we do this 27 times 3. And then we have k, at last we have kabc is the sum over I equals to minus 1 ki, what is it, b, c, I minus u by the power of a, 27 times 3. So, and of course, I mean, thinking about this 10 minutes, you should all come up with this, because of course this is completely true. Yeah. So, first of all, that you notice that the number of operation is kind of, it's now 9 times, sorry. Yeah, so it used to be 27 times 27, so it appears to be 3 times less, right? And I also believed that it is 3 times less until I counted the operations and recognized that in between we also have the terms over which we sum, they are also shorter. Yeah, so it's a little bit more involved. So since each term, let me write this down in the mirror transformation has fewer operations, than in the naive form. The savings are even higher. So, and I was no longer able to figure this out theoretically, but what I did is I used the computer algebra just to count the operations and compare them. So, and now what we have in the naive way, we have additions. So the naive way has 1,482 additions and multiplications. It has 1,452. The Chimera has 270 additions and 162 multiplications. Yeah, that's a pretty significant difference. So only 1/5 the number of operations required. Okay, it's always interesting that the most trivial things do the biggest difference, make the biggest difference. Yeah. So, however, actually, this is not the best part of it. There's something more important than to save 80% of your compute time, namely that you actually compute the right thing. And the problem with this long central moment transform is there is a lot of summation, and it produces a lot of round-off errors. And this now has changed here because this Chimera transform automatically is a pairwise summation. So you can, you should sit down and rearrange these few operations that you still have in an appropriate manner, still by hand, optimizing by hand. And after you're doing this, and you compare the results, then you will actually find that the single naive transformation, so just going one way and back, this has been observed. Of course, this is not always the case. So what I've done is I picked from a simulation the populations, wrote them out, and did one transform one way and the other, yeah. And so I did the transform forward and backward and compared this to when I didn't do any transformation, yeah. So because when I do the forward and backward transformation, they should not change, right? And of course, the Chimera transform has a round-off error, but this round-off error is different from the naive transformation. And in fact, the naive transformation can lose up to 10 significant. So this is what I have observed. I mean, there's no proof that this is often the case or something. This was just in this particular case. Yeah, but this is what I observed. I could use 10 significant bits more. It's not that the Chimera transform is perfect. Yeah. But one transformation can lose 10 significant bits more than the Chimera transform. In single precision, 10 bits is half of your precision, right? So one transformation kills half of the precision. Yeah, so what the test has done is we take an arbitrary node from an actual simulation, and we do the forward transform, and then we do the backward transform again, and see how many bits are different from the populations. Yeah? And these were 10 more than in the case of the Chimera transform. Yeah, and since the Chimera transform itself is not perfect, yeah, you can think what this means. Of course, when you already lost so many bits, then the next time you will lose again the same number of bits, so that it's not. It's not so bad that you do 2 transformations and then everything is gone. Yeah, that it's not that bad. But actually, what it rather means is, if you do this naive transformation in the first place, you're only using half the precision that is actually available to you. So if you do double precision, you actually effectively calculate in single precision, right? And no, that's not true. No, this is because it was 10. Okay, so this was too naive. Now you're losing 10 bits, and if you have double precision, then you should have something like, I don't know, how many bits do we have in double precision? I don't remember. But I mean for the fraction, 52. Okay, so right, so you would still have 42 left, right? Yeah. Anyway, so it's not, it would still be better than, okay, yeah, double precision would still be better than than single precision in this case. Okay, so this was the topic round of errors, and because I was asked to, I'll add here in the last half hour or so one more topic about the implementation, and this is the esoteric twist. Now, this has nothing to do with cumulants and with computation in itself. This is related to the streaming. Now we have talked about the collision, and also the streaming has to be done in an efficient manner. So what we have already seen in the example code that we had is that we can combine the streaming with the collision. And that should always be done, because otherwise it becomes pretty expensive. Because as I told you, reading the populations is the most costly thing actually in the entire thing. So if you split this up and do collision and streaming separately, you almost double your execution time. Yeah. So this means what we want to have a read once, write once, instead of reading once and reading twice and writing twice. Yeah. So, and now we have seen the thing that we have seen in our example was the so-called push scheme. Where we write to the neighbor so this is how the example code was implemented. So we have fi x and we go no comma plus ei delta x. So we go to the neighbor in the next time step, and here comes, so okay, I now want to write that the collision is in the same step. I'm not completely sure how I should write this, so I put a C, yeah, so this is the outcome of the collision applied to fi that we read from the current location in the current time step, right? So we take fi, apply the collision, and then we move this to the neighbor, right? So this is the way we implemented this. So this is the push scheme, and it is an A so-called A-B pattern, because we read from a population B and then we write it on a population A. And after we've done this, we exchange pointers from A to B. Yeah? So this is the swap. So we always need two populations. So an alternative to this is the so-called pull scheme. This is the read from your neighbor. So read from your neighbor looks like this. You have fi at the position of the nodes for the next time step is equal to the collision operator applied to fi if the populations coming from the neighbor. So now they are coming from the neighbor. So now we have to get them, of course, from the opposite direction. Yeah. So here we had x plus, so we pushing them, and here we pulling them, so we go one step backward and get them out here. Okay, and after this, again, we do the swapping of A and B, because here we have, again, B written onto A. So these are so-called A-B pattern methods. Question, what is better, pull or push? Who is for pull? Who is for push? Okay, not too many have an idea, an opinion about this. It may depend on your hardware. That's the short answer. However, there is reason to believe that most hardware is faster in reading non-aligned than in writing non-aligned. Yeah? So in particular, this is the case for GPUs. So in GPUs, reading non-aligned is not a problem, but writing non-aligned is a problem. So reading, so what do I mean by reading aligned? Reading aligned is you read things from one spot, yeah, all together. So you read locally, so to speak, and you write, far apart, yeah. So this is when you push things. So in this case, especially on GPUs, pulling is better than pushing, but it depends on your hardware, yeah. Okay, say if you don't know, then pull often faster than push. We did push because this was simpler to implement in our example. And it may not be a big difference. So non-aligned read is less expensive than non-aligned writes. So now this push and pull, as I said, are both A-B patterns because they require patterns. Reading from B and writing to A. Then reverse order. So, I mean, this is not very surprising because this is also what you would always do in a finite difference or also finite element code. So you'll have a state vector from the lost time step and you go to a state vector of the new time step. However, there is one significant difference between, say, a finite difference and also finite elements and the Lattice-Boltzmann methods. And this is that if you think about finite difference, for example, because it's the simplest example, the state of your variable, say the state of the variable u, in the next time step also always depends on a finite neighborhood, because you have to calculate, you always have to calculate some finite differences. So you always have a mapping from many variables to few variables, right? In each of the single operations. Lattice-Boltzmann is kind of a little bit unique in the fact that it always maps Q variables to Q. Yeah? So the amount of variables that go into the collision is the same that go out of collision. And this already implies one thing. If it writes as many variables as it reads, this absolutely implies that each variable is read only once during the computation, no, not twice. Yeah? Otherwise it doesn't fit, right? And therefore, it is different from finite differences where you still need the variables from the previous time step for the other nodes around it. In Lattice-Boltzmann, whenever you read a variable, it is no longer required. You can immediately override it. Yeah? However, you have to do this in a specific way, because actually you want to push them. If you push them to your neighbors, you would override the next time step. So you have to do it in a clever way. And these clever ways, where we do streaming, streaming by overwriting the previous state, they are called in-place streaming. There are several algorithms that do in-place streaming. The one that we are looking here is the ESO-twists algorithm. So first of all, okay, let me write this down. So the collision, no. So the collision has R, say Q, reads, and it goes to RQ writes. So we always read exactly the same amount of data that we also write. So in principle, we can discard all the variables that we've once used. So the question is it possible to write from A to A? So this is an AA pattern. Using only one array. So as I said, there are several ways of doing this. They distinguish themselves in particular way. So I'm not going into the other algorithms. I'm just showing one here. Say we have our information stored in arrays, yeah, according to their direction. This can be done in a different way, but now assume this for this operation here, and say there is data A, data B, and data C. And we are not now specifying what direction this is for the time being. So they are stored here in accordance to X. So we're assuming now this is one-dimensional. This can be done for 2 dimensions too. And we have the node N. Say this is the position for which we now want to read our data. And we read this now twice from the position N, and once we read it from the position N plus 1. Okay, we are going to see what this means. Now we distinguish between even time steps. So in an even time step, we read the F minus 1 population from dA N plus 1. We read the F0 population from dB at the position N, and the F1 we read from dC at the position N. Then we do the collision and do the write. We write dA at the position n plus 1. So it's important, we can only write to positions where we previously read from, right? Otherwise we would overwrite something from another node. So, but in this data point, we do not store the population f minus 1, but we store the population f1 after the collision. In the position b, n, we store f0. f0 is the thing that is not moving. Yeah? So we write this back here, and in the position c, and we write f minus 1. So by having done this, we have actually moved the population f1 one step in positive direction and f minus 1 one step in negative direction. Yeah? So we did the streaming. However, we reinterpreted the direction. So previously, dA was going in the negative direction, and now dA is going in the positive direction. So this was in an even time step. Now comes the odd time step. Odd time step. So now we have to have, so here's the read. Now we have to have the opposite interpretation, right? So we take f minus 1 is of course now dc n plus 1. So you recognize we wrote f minus 1 into dc. Now so we have to read it from dc again, yeah? And we read it again at the neighbor further away. It's here. Right, the f0, there's no change. This is always db n, and f1 we write as dan, we read as dan. Then we do the write afterwards, Now we write to dc n plus 1, we write f1 after collision, db n, we write f0 after collision, and to dA we write n, we write f minus 1 after collision, and by this we are back to the original state. So what we do is we read one of the populations from one side, yeah, from one of our neighbors, and we write everything back in reverse order. And then in the next time step, we exchange also by swapping, yeah, the arrays or the positions of the data A and the data C, and read this again now in the opposite order, and by so we are moving data around. So this is not the only way this in-place streaming can be done, but this in-place streaming has some advantages regarding the bookkeeping in particular. Yeah? And in particular, the bookkeeping for the case when you have indirect addressing, which we have, for example, in Virtual Fluids, the GPU version. Yeah? So if you have indirect addressing, and so indirect addressing means you don't store your data in an array, in a big matrix, but you do the communication with the neighbors by having links or pointers to the neighbors out of each node. Now the interesting thing with esoteric twist here is that it always only requires a neighbor to one side and not a neighbor to the other side. So usually you would have to know what is your left neighbor and who is your right neighbor. Yeah? In that case, you only need to know who is your right neighbor, and you never need to know who is your left neighbor. Yeah? So you save the memory and to keeping to do the bookkeeping of who is actually your neighbor, right? So, for example, if we now do this in 2D, of course we are doing it in 3D, but this is even more significant then. We do this, okay, let me draw this a little bit further down here. No, it's even further down. So, how do we store? Say then we have here the node itself on which we do the read. And from this node, we read populations that go in these directions. Yeah? So then in this, so obviously for the cardinal direction, yeah, as we had before, we read the one that come down here, but we also read these, and from this above here we read this population. So what we need to know, so this node here needs to know 3 of its neighbors. Yeah, so it needs to know the one in y direction and the one in x direction. And actually, if you think about it, this node here also needs to know the one in y direction. So actually, the node here, the original node from which we start, does not need to know the one in the diagonal direction, because it can always follow, yeah, the path. I mean, the pointers. So you have a pointer in y, and you have a pointer in x, and then obviously this node again has a pointer in y again. So you can come, and also it has this also has a pointer in x again. So you actually have 2 possibilities to, without knowing the neighbor in the diagonal direction, to actually go to the neighbor in the diagonal direction. So all you need to know is two of your neighbors. Actually, and we have never implemented this, but if you think about this, you can put them in an array according to one direction, right? So in this way, you would only need to know one neighbor. That would be sufficient, or in 3 dimensions, you would need to know only 2 neighbors, which is, if you compare it to the fully linked list where you need to know 26 neighbors, yeah, makes a lot of difference in terms of memory. Yeah. Okay, I've not drawn the right version here. So when we do the write back, what we do is we write the populations that go, of course, in like exactly the opposite way. So this is done in this way here. So this would be this here is the write, the read, and the other one is the write. So, as I said here, just writing the few sentences down. Access to neighbor only required in positive direction. So this means we have a low bookkeeping cost. For indirect addressing. And the other thing that is important, so this thing here is because it writes only to where it read from. Yeah, this means it's completely thread safe. It's also important because it means that all the lattice nodes can be executed in arbitrary order without disturbing any other lattice nodes. The only thing is you have to know when the time step is over and when you can do the next time step. Yeah, this is the only thing actually here required to know. Okay, so this was now the lecture on efficient implementation, where we talked about round-off errors, so conditioning. Yeah, we introduced the Chimera transform, and we also talked about the thread-safe in-place streaming that we can do with esoteric twists. Okay. My name is Martin Geyer. In this course, we'll have a deep dive into the Lattice-Boltzmann method. Into the theory, we start from kinetic theory to understand how the equilibrium is derived. Then we will study in detail asymptotic analysis and its use for developing a high-fidelity Lattice-Boltzmann methods. We'll see that the usually used MRT methods has some drawbacks, and these drawbacks can be overcome when we use cumulants instead of moments in this method. We will also discuss about grid refinement and implementation details. There's included some exercises using some simple code, and we'll also introduce the open source Lattice-Boltzmann code virtual fluids. Was this 2 minutes? Okay. I'm not redoing it, even if I'm not good. I mean, and it is not my job as talking as a. I'm not a newscaster, right? So I may not talk beautifully. Yeah.
That's fine. I think it's bad actually. Hello, welcome to this Gian course on high fidelity lattice bone spell methods from theory to practice. My name is Kameshwar Rao Anupindi and I am the co-instructor together with Professor Martin Geyer. In this course, I'll be demonstrating some of the programs that we kind of learn in the theory part, and this will be related to the streaming and collision, calculation of the equilibrium distribution function, and then the overall single relaxation time BGK code and the lid-driven cavity code. Okay, so we will demonstrate the C++ Python interface and then how do you run them, and then look at the output, compare, and then perform the validations. That's all. Thank you.
Okay. So that's then really it, I believe.
Yeah. So we got the certificates. While you have your tea, we will try to get them and then